1020. 1020. Have you got the president's location? Yes? Aha. Okay, you know exactly where he is. It's now 8 o'clock. Okay. It's now 8:10. Do you know exactly where the president is? Ah, okay. We're okay then. The president is home. Calling number 5, where are you? It is 100. Bleak, lack, blook. Now it is 110. Where are you? Luck, blook, lack. Oh, where are you now? It is 120. Till tooth, luck. Okay, so to describe Obama's location, we need 2 pieces of information. We need to know how far east or west he is and how far north and south he is. So if this dot represents where his little tootsie is, then we need x of t to tell us how far east or west he is, and we need another function, y of t, to tell us how far north or south he is. In this case, x of t is 9th Street and y of t is Constitution Avenue. Now, on the other hand, our little flying saucer friend, to locate him, we need 3 pieces of information. We need to know how far he is right or left, up or down, and then towards you and away from you, because this is 3-dimensional space after all. And so we need x of t, y of t, and z of t in order to describe his location at any particular point in time t. So let's look at a math example. These equations are called parametric equations. Now, what does parametric mean? Let's look in a dictionary, and we'll look up the word parameter, which is a noun. Parametric would be the adjective, and this noun means determining factor. Now, since t, which is time, determines the x and y position of the president, or for that matter, any other moving object, t is the parameter, the determining factor. Now, back to our example. We need to plot some points. So we need a t-chart. Let's pick a few t-values, and because I happen to know what this is going to look like, I'm going to pick t-values that will work well. But if you're doing a problem, you just pick any you feel like. And then we'll compute x and y. Now make sure you choose some negatives and some positives for t to get a good picture. So, for example, when t is -2, we get x equals -2 squared plus -2, which is 4 minus 2. And y is 2 times -2 minus 1. Now, for t equal -1, we get -1 squared minus 1 for x, and 2 times -1 minus 1 for y. For t equal -1/2, fractions, we get a positive 1/4 minus 1/2 for x and -1 minus 1 for y. And for t equals 0, we get x equals 0, y equal -1. For t equal 1, we get x equal 2 and y equal 1. If we plot these 5 points and connect them with a smooth curve, we can see that these equations describe an object traveling along a parabolic path. There's the point 2, -5 at time t equal -2. There's 0, -3. There's -1/4, -2. 0, -1. And finally 2, 1. Notice that we need arrows on the graph in order to show the direction of the object's path as time flows from negative to positive. Now, a lot of people wonder and ask me, well, how can time be negative? Well, t equals 0 is arbitrary. For example, maybe t equals 0 is noon. That means that a negative t value would be sometime before noon, and a positive t value would be sometime after noon. So yes, you can use negative numbers for time. To reiterate, t is called the parameter because time is the determining factor, and it's called an independent variable, whereas x and y are called dependent variables because their values depend upon what you plugged in for t. Now, three-dimensional graphs are more difficult, but let's take a look at a few anyway, just for fun. What geometric form is the graph of ax plus by plus cz equal d, where a, b, and c and d would be numbers? Did you say it's a line? Well, a lot of people think that that's a line because ax plus by equals d in 2 dimensions is a line, but let's look at an example with actual numbers. In this equation, what would z have to equal if x and y were both 0? I hope you said 2. What if y and z were both 0? Well, then x would have to be 3. And finally, if x and z were 0, y would have to be 6. Now, if we graph these points on a 3D grid, we can clearly see that they are not forming a straight line. Notice that, for example, 1, 4, 0 would also satisfy our equation, and in fact, any point on this tilted plane would work. Now I have a question. Why do you suppose I'm only drawing a triangular portion of the plane? Why is that a good idea? Why not draw the whole thing? Well, I'll let you mull that over. So, in conclusion, a single equation in 3 variables will describe a surface, not a curve, and not a path that an object moves along. For example, x squared plus y squared plus z squared equals 9 represents a sphere of radius 3. You can see that this makes sense. If you omit the z squared, you've got your old friend, the circle. So a 3-dimensional circle is a sphere. Surfaces are very hard to draw by hand, especially complicated ones. Here are some surfaces drawn by a computer. Oohs and ahs would be appropriate here. Ooh, ah. The only way to describe a curve or a path of an object in 3 dimensions is parametrically with 3 parametric equations. Here are some graphs of curves in space. Again, these are generated by a computer. There are 2 curves here. One is a spiral and the other one is circular. There's a curve drawn on a surface called a saddle-shaped surface. And here's a curve drawn on a flat surface compared to a similar curve in 3 space drawn on a curved surface. But in this lesson, we're going to concentrate on a 2D example. So back to our 2-dimensional example, we can do something we can't do in 3 dimensions. Eliminating the parameter means finding a direct algebraic relationship between x and y. In other words, one equation. Often the best way to eliminate the parameter and create one equation out of the 2 is to solve for t in one equation and then substitute that quantity that t equals into the other equation. I'll show you what I mean on the next slide. Which equation above would be easier to solve for t? I hope you said the second one. To solve for t, we need to add 1 to both sides and then divide by 2. Now, substitute y plus 1 over 2 for t in the other equation, the first equation. Technically, we're done at this point. All we were asked was to get one equation without a t in it. T has been eliminated, but our equation looks a little messy. So let's play with it a bit. Square that first term out. Then, I don't like to work with fractions, so I'm going to multiply both sides by 4. Collect like terms. Oh, my goodness. The right side will factor really well. Might as well do that too, and divide by 4 while I'm at it. That last form of the equation shows clearly why the path of the object goes through -1 and -3 on the y-axis. Cool. This process of eliminating the parameter and creating a single equation is not possible in 3 dimensions. Why not? Why can't you do it? I'll let you ponder that question. Oh, I can almost hear the cheering now. We can do these graphs on our calculators instead of by hand. Yay! But you need to be in a good mode to do that. Let's put our calculators in Radian mode because later we might look at parametric equations with sine and cosine in them. And most of you are probably in a funk. that is FUNC for functions. So you need to arrow over and hit enter to change to PAR mode. What do you suppose PAR stands for? Yep, parametric. You are right. Now let's set our windows all to the same values so that all the screens will look the same. T should go from -10 to 10. These are good default values to use. Your T step should be about 0.13. That's the calculator's default value. And for this particular graph, I chose X to go from -1 to 3 and Y to go from -6 to 2. And this is only because I knew what the graph was going to look like. When you're doing other problems, you'll just have to kind of guess and then adjust if necessary. Warning, warning, make sure that your T-step is about 0.13. That's 0.13. Anything bigger and your graph's going to be a big mess. Why is that? Well, you need to think about what T-step means. It's the increment. It determines how close together all the points on the calculator will be. Why is it going to be a mess if that value is too big? Okay, make sure you don't have any typos. And we're going to move on to the next step. Press your Y equals button. Type the equations in, and you'll notice that your X button has magically changed into a T button. Do not use your alpha buttons. That won't work. Just use your X button, just like you used to do on regular function graphs. Now, one more little cool thing before you hit graph. See this little circle here? I want you to arrow back behind X sub 1t and hit enter. I think you have to hit it twice until you see a little dash with a circle after it. This option makes your calculator graph the curve in a very, very cool way. All right, hit that button. See the little circle? It's like watching somebody's head from above as they walk along the parabolic path. That's pretty cool, huh? When we draw a parametric graph on our own paper, we need to include arrows in order to show the direction that the object traveled as t increased. Now, that's a nice picture. Don't clutter up your picture with lots and lots of arrows. 2 or 3 are sufficient. So, now it's your turn. Here are some interesting parametric equations for you to graph. You may want to stop the video here and copy them down. The solutions will show up after the credits. Have fun!